friends, in this video we will see an important relation between continuity and integration. Here we show that if function is a continuous, it is also integrable. Secondly, we prove that if a function is a monotonic, then that function is also integrable. So first, suppose that f is continuous on closed interval a comma b, and let we have an epsilon greater than 0 be a given number. Depending on this number, we choose another number eta such that eta into b minus a is less than epsilon. Now you can see that if we have two different numbers, suppose one number is 100 and second number is 50, then we can choose that this eta is a different number such that, suppose if we take eta equal to we can choose a number 1 by 3, then 1 by 3 into 100 is become less than 50. So likewise we have chosen this b eta is such that b into eta into b minus a is less than epsilon. But as f is continuous on closed interval a comma b, it is uniformly continuous. Function is uniformly continuous on closed interval a comma b. As function is continuous on closed interval, we have a standard theorem. If function is continuous on closed interval, it is uniformly continuous on that interval. So for a given epsilon, there exists a delta, therefore there exists a delta greater than 0 such that for a partition p equal to x0 to a up to xn, this is my partition, and this partition is such that this mu of p is less than delta for mod of f of t1 minus f of t2 is less than eta, where t1 minus t2 is less than delta, where t1 and t2 belongs to any points of the closed interval. So this is by the definition of uniform continuity. By uniform continuity, the difference between the values of the function for any two points is less than eta whenever these points are less than delta. Now we have chosen this delta, this is such that we are choosing the partition p is such that this mu of p is less than delta. Then as all the values of the functions lies between this the values are less than eta, we have capital Mi minus small mi is also less than equal to eta. But we know that UPF minus LPF, what is the UPF minus LPF? This is equal to summation of capital Mi minus small mi into delta xi, I is equal to 1 to n. But all these values, okay, this value is less than eta, therefore supremum, their difference of the supremum and infimum is also less than eta, and this gives me we put an greater value, therefore this is less than equal to eta into delta xi, I varies from 1 to n, okay, and eta is not depending on summation, so therefore we can write eta into summation of delta xi, I varies from 1 to n, but this is eta into summation of delta xi is b minus a, so eta into b minus a, but eta into b minus a is a less than epsilon. That means we have UPF minus LPF is less than epsilon, and by the condition of integrability, if upper sum minus lower sum is less than epsilon, the function is an integrable function. So friends, whenever the function is continuous, the function is integrable function. Now second result, we show that if the function is a monotonic function, monotonic means either it is an increasing or decreasing, the function is integrable. So the result is, the statement is, if f is function, f is monotonic on closed interval a comma b, then it is integrable. So let us consider the case of increasing function. Consider f is monotonically increasing. As function is monotonically increasing, that means if my function is f of x equal to x square, very simple function, and it is a 1 to 3 suppose, then f of 1 equal to 1, f of 2 equal to 4, f of 3 equal to 9, right? So this is a minimum value, this is a maximum value, and all the values lies between 1 and 9. So if function is monotonically increasing, therefore clearly f is bounded function. All the values of this function lies between f of a and f of b. And let epsilon greater than 0 be given. Now again, as like in the previous theorem, we choose eta such that eta is less than epsilon divided by f of b minus f of a plus 1, like this. Okay, we can choose this eta. Now friend, you can see that if this is the interval, then minimum value of this is 1, function value is 1, and maximum is 9. This is my capital Mi and this is my small mi. So if we calculate the upper sum minus lower sum of this function, then this is summation of capital Mi minus small mi into delta xi, I is equal to 1 to n. But what is this capital Mi? Capital Mi is, this is nothing but function f of this is, if interval is xi minus 1 to xi, then minimum value we get it as f of xi minus 1, and maximum value we get it at xi. So we have, this is summation I is equal to 1 to n f of xi minus f of xi minus 1 into delta xi. Now again applying the function is a monotonic, therefore for epsilon greater than 0 there exists a partition P x0, x1, xn with norm we take mu of p is less than eta, right? This is our choice of eta. Now mu of p, maximum length of this subinterval, is less than eta. That means this value is less than eta. So let us put here eta, maximum value, and therefore summation of f of xi minus f of xi minus 1 is into eta, but eta is independent of this, I is equal to 1 to n. So this gives eta into summation of f of xi, that means here if we take x1, f of x0, instead of this we write all these values, plus f of x2 minus f of x1 plus f of x3 minus f of x2 plus f of xn minus f of xn minus 1. Now you can see that this x1 and this x1 get cancelled, x2 get cancelled, every value get cancelled, and we have this upper sum minus lower sum is less than eta into f of xn minus f of x0. Okay, but what is f of xn? F of xn is f of b. this is eta into f of b minus f of a. Now let us put a greater value for this eta. Eta is less than epsilon divided by f of b minus f of a. So epsilon divided by f of b minus f of a plus 1 into f of b minus f of a, right? Look at this value, f of b minus f of a divided by f of b minus f of a plus 1, that is like 3 divided by 4, 4 divided by 5, 10 divided by 11, and you can see that this is an fraction value. So whenever we multiply any number, suppose we are multiplying 10 by a fraction value, that is 1 by 2, then we get 5. That means when we multiply any number by a fraction value, its value becomes smaller. So we are multiplying this epsilon by this fraction value, therefore the value of epsilon becomes smaller. That means epsilon is greater than this number. Okay, but what then we get? Upper sum minus lower sum is now less than epsilon, and upper sum minus lower sum is less than epsilon. By condition of integrability, function is integrable, and that means the monotonic increasing function is integrable. Similarly, we can show that monotonic decreasing function is also integrable.